Welcome to the final video on the wave equation in the wave, heat and Laplace equation series. In this particular example, we are looking at what to do if we get a final non-homogeneous initial condition that looks something like this here. So if we walk through the whole separation of variables, we're going to get a u of n that looks like this, and that satisfies our three homogeneous conditions. And now if we go to do exactly what we've done in all the previous videos, where we put in this last condition here and set t equal to 0, and we try and solve for a of n, we're going to end up with this down here. The problem with this is that we have previously defined a of n to be a constant. So if we solve for a of n there, we're going to get x over cosine n pi x over l. So the problem here is that a of n must be constant. So we need another way of doing it. Now the solution to this is to use the superposition principle and a Fourier series. Now there's other videos out there on YouTube and around the place that go into more detail on what the Fourier series is, but really quickly it's just a way to decompose something, a function, say x, into sine and cosine functions, which is what we want. Remember, if this up here was like a sine something, we wouldn't necessarily need to use this Fourier series here, as it has been in all the previous examples. So what we're going to do is we're going to use because we've got something that looks like this here, we're going to use the Fourier cosine series. So that looks like this. So I'm already keeping the initial condition where t equals 0. A naught over 2 plus summation n equals 1 to infinity a of n cosine n pi x over l, and that should equal x. So this is the Fourier cosine series. If we had I might do this in green, there is also a Fourier sine series, and if we had a u of n that looked like a of n sine n pi x cosine n pi ct, and we had a non-homogeneous initial condition where u of n x naught, so when t equals 0, equals a of n sine n pi x, and that is supposed to equal x. You'd see in this case I would use the Fourier sine series. But for this particular case, we're going to be using the Fourier cosine series. So we've got this here. And what we need to do now, so all I did here was just use the Fourier cosine series, and that is this thing in here. Right, so now our goal is to find a naught and a of n, they're constants. So to find them, we're going to be using the Euler formula. So using Euler formula, find a naught and a of n. So a naught equals 2 over L, 0 to L in this case, x dx, and our A of n, write that here, A of n will just equal 2 over L, 0 to L, x cosine n pi x over L dx. So that's just the Euler formula. So I haven't done anything magical there. I'm just using the Euler formula. You can look that up online if you don't know what it is. So all we need to do now is compute these two integrals in order to find A naught and A of n. And then we'll just plug them back into our solution and we'll get the specific solution. So in this case, you can work these out for yourself, but you can see that pretty easily that just equals L. For A of n takes a little bit more working. So I'll do that down here. Using integration by parts. Or the DI method. It's you can see that's clearly based on integration by parts. I'm just going to use the DI method here because it's just fairly straightforward and quick, but I'm assuming that you know how to do integration by parts or integrals of this nature. So x1, 0, cosine n pi x over L. That will be L over n pi sine n pi x over L. This will be minus L squared over n squared pi squared cosine n pi x over L. And put them together. We're going to end up with something that looks like this. Don't forget the this constant out the front here. So 2 over L xL over n pi sine n pi x over L plus L squared n squared pi squared cosine n pi x over L, and that's from 0 to L. Further working, simplifying, what do we end up with? L squared n pi sine pi n plus L squared n squared pi squared cosine n pi, and that's going to be minus L squared n squared pi squared, and you'll see that this sine term here will vanish because n is an integer, so pi of n will just end up as 0. So this will end up as 2 over L. Simplifying it further, L squared n squared pi squared cosine n pi minus L squared n squared pi squared. Aren't integrals fun? What's further here? We can do 2 over L. Simplifying further, L squared over n squared pi squared, minus 1 to the n, minus 1. The minus 1 to the n, that's simply, if I do this in green, the cosine n pi just equals minus 1 to the n. So you'll see that on the unit circle, if we have 0 here and pi here, that at n equals 0, will equal 1. And at n equals 1, we'll get minus 1, and at n equals 2, we will get 1, and then we'll get minus 1 and 1, and so on with that. And with that, so we can just rewrite it. So go back to pink here. And simplifying that further, oh, we're still in green, we get 2l over, that cancels with that, 2l n squared pi squared minus 1 to the n minus 1. And then simplifying that even further, we will get minus 2l over n squared pi squared, and we'll get 2. That's multiplied by 2 if n is odd, and 0 for n being even. So now we can, this is actually our a of n term here, and up here we have our a naught term here. So now we can go and plug this back in to our u of n here up the top. So or maybe we should simplify it further. Yeah, maybe we simplify it further. Okay, so we can write every n. We can write every n as 2n minus 1, because that's ensuring that it's odd, because remember we only have this term if it's odd. If n is even, it all goes to 0. As n must be odd, and we can, when we come to write the final solution, move all constants. So in this case, we've got L and pi outside the summation. That's just really putting it in the standard form that you would write it in. So now our specific, I will delete this. So our specific solution will look like this. Equals L over 2. So remember that was the a naught. Minus 4l over pi squared summation. So they're the constants that we've moved out the front. N equals 1 to infinity of 1. And this is the n. So remember the n squared here that we'd normally have, we're going to write as 2n minus 1 squared. And now we've got our cosine. Remember this was n pi x over L. So we're going to write 2n minus 1 pi x over L. And cosine, this was n pi ct over L. So we're going to write 2n minus 1 pi ct over L. So that is our specific solution. In it, we've used the superposition principle, we've used the Fourier cosine series, and we've also used the Euler formulae as well in here to find a of n and a naught. And then we've really just plugged it back into what was our u of n here, up here. And yeah, that is our final solution.